Okay. So, we are looking at forward chaining rule based systems and so on. In the last class we saw how rules are essentially matched with data. Today we want to look at how one decides as to what is a rule that is going to be fired next essentially. And in doing so, we also want to come up with a view that what we are looking at is language called OPS5 is a programming language. So, a word about the word OPS5. So, it came, as I have been saying, this whole work came from Carnegie Mellon University, CMU, started by Simon and Newell, and various people worked on it. So, this OPS5 basically stands for official. Some people say it stands for this production system. Language, and it gradually evolved over a period of time. It became something called OPS83, I think in 1983, and eventually transformed into something called SOAR, which some people say is more than a programming language in the sense that it is a cognitive architecture, and maybe we will give you a tutorial on SOAR at some point. Let us come back to the thing about looking at this as a programming language. So, what are we looking at this programming language? What OPS5 does is that basically it implements it is an inference engine which has this match, resolve, execute cycle, and the match part, as we have seen, is made efficient by using the Rete network, but right now we are not really concerned about that. We are concerned about what kind of a language can we think about it, what paradigm does it follow essentially. So, if you look at the languages that exist, we have imperative languages, like C for example, and how does one program in an imperative language? That the programmer has to state what are the actions to be done in the order in which they have to be done. So, control is directly into the hands of the programmer, and the programmer has to simply say that do this, then do this, then do this, then do this, and so on and so forth. Of course, in the process you can put in branching and you can put in loops and you can put in all kinds of things, but it is basically an imperative language. It tells the machine that this is what is to be done first, then next, and then so on and so forth essentially. Then we have seen object oriented programming language, which, as I am sure you are familiar with, languages like C++ and Java, but there were other earlier languages like Simula, and like all good things, object oriented language also came out of work done in AI. A little bit later in this course we will look at something called a scheme called frames, and those frames essentially gave rise to what we now call as object oriented systems. Basically, the idea of inheritance and all that is automatically taken care of in such systems. Then there are languages like logic programming languages, which are in some sense close to what we are looking at right now. But logic programming language is a pure logical theorem proving language. Here our language says that you have the left hand side which you have to match, but the right hand side is a set of actions essentially. Whereas logic programming tends to view the whole exercise of programming as theorem proving essentially, and we will see maybe a little bit later how that is done essentially. And what we are studying is, as we have said, pattern directed systems or data driven systems. In the sense that what happens next or which command is executed or which sentence is executed depends upon the data. It is the data which derives the execution. Of course, you might argue that if you have a lot of if statements in a imperative language, then essentially control there is also driven by data, but the programmer has to hardwire that control into the program essentially, whereas in the language that we are looking at it right now, this is not the case. So, let us see what is happening here. We have the match phase that we have studied so far, and what it produces is a conflict set, which is essentially a set which contains pairs of rule 1, let us say, data 1, and this data itself is a set. So, let me put it in as a set. So, there is more than one pattern that a rule is matching, then rule 2 with its matching data, and so on. So, let us say there are n rules. This is input to this phase called resolve. So, what does it resolve? It resolves the conflict between matching rules. So, at the end of the match phase, you have a whole set of rules with matching data, and you can sort of try to visualize it that all of them are clamoring to say execute me, execute me, execute me, and so on. It is like getting a party ticket for elections, and it is a task of the resolve phase to decide which rule to execute next essentially. So, we want to look at that in today's class, and you can see that this basically embodies the problem solving strategy. So, we want to look at different strategies and see what will they give us essentially. So, we want to look at this process of conflict resolution. Which says pick a rule with its matching data from the conflict set essentially. So, what are the different strategies? One property that we always want to follow is called refractoriness. This says that once selected, the pair is removed from the conflict set essentially. In other words, what it means is that let us say there was a rule which got selected, and let us say it had 3 working memory elements that it was matching, and it got selected based on whatever selection strategy that we will look at in a moment. But having been selected and having executed that rule once, obviously if those 3 working memory elements are there in the working memory, this rule will still be matching essentially. Refractoriness says that never execute the same rule with the same piece of data essentially, only once. It is like money essentially, once you have spent it, you have done with it essentially. So, if you have a rule with some, remember that working memory elements are identified by timestamp. So, if there is a rule which is matching a data with let us say some distinct timestamps, it can fire only once. The only time it can fire with the same data again is that if one of those working memory elements is deleted for some reason and inserted sometime later in life essentially, in which case it would have a different timestamp, and then of course, it may come into contention again essentially. But otherwise refractoriness says that with the same inputs you fire it only once essentially. So, the term actually comes from looking at neurophysiology, where people observe that as neurons they have input building up for them, they can fire once, but having fired once they cannot fire immediately again essentially. So, there is a latency between one firing and the next essentially. So, that term is borrowed from there, but essentially this is as far as we are concerned simple common sense, and it simply says that if you have already done what those rule is saying, do not keep doing the same thing again and again essentially. If you are doing a classification problem, then you are looking at the data of a certain class. So, let us say you are grading students. So, if you have seen a student with marks 75 and attendance good, and you have said grade is equal to let us say A, then do not reassign the grade A again and again. Once you have done with it, you are done with it. So, this refractoriness takes care of that essentially. Then you could do it in order. Or sequence in which rules are stated. That you can say, okay, I have an ordering of the rules, and of the matching rules I will pick that rule which is first in this order, highest in this order or something like that. So, obviously, this gives control to programmer. The data has no impact on which rule will get selected. The programmer has said that if these rules are in contention, always select this rule essentially. And we will see later when we look at Prolog, which is a programming language which is based on the logic programming idea, that in Prolog you have to carefully write your statements in a careful order if your program is to execute properly essentially. And that is because, as we will see, Prolog essentially does processes the statements in the order in which you write them essentially, which amounts to doing depth first search in some space essentially. But we are interested here in a different approach, which is that it should be decided by the data essentially. Incidentally, Prolog does not do forward chaining, it does backward chaining, and it kind of embodies a totally different problem solving strategy, which is goal directed essentially, as opposed to pattern directed that we are here, that the data decides what will be done next. In Prolog, the goal decides what patterns you will look for essentially. Anyway, we will come to that later. So, these are two basic strategies. Then there are more interesting strategies. One is called recency. So, this says select that pair So, remember whenever I talk about the pair, I mean a rule and the corresponding data, which has the highest timestamp data. So, I should say really working memory element. In other words, most recent. And what do we mean by most recent? Not the most recent working memory element. Amongst the data which is matching, amongst the working memory elements which are matching all the set of rules, amongst those rules whichever is the most recent ones, and select that rule which matches the most recent element. What is the advantage of this? If you think of this intuitively, it allows you to maintain in some sense chain of thought, whatever that. Or maintaining a line of reasoning essentially. In terms of logic, if you have just concluded something, or if you added a new working memory element which will have the latest timestamp, if there is some rule which is using that, prefer that rule essentially. So, in that sense whatever changes you are making, so you can see that that the most recent working memory elements will get attention more essentially. And then another important strategy is called specificity. This says select the rule or select the pair with most specific data. And what do we mean by this? We basically mean most number of tests. So, select that rule which is looking at more data and for deciding whatever action has to be done essentially. And there is a combination which is used in OPS5 which is called MEA, which stands for means ends analysis, and it says the following, that recency for the first pattern in the rule and tie breaking by specificity. So, what is this strategy saying? This strategy is saying that okay, you have got a set of rules with matching data, pick those rules whose first pattern matches the most recent data essentially. So, this if you go back to this idea of context that we talked about when we were talking about XCon, you set the context, you are building the foundation, then you are filling the walls and so on. So, the moment the first pattern in every rule would match the context, and the most recent context is the one which would be considered, the others would not figure, because this says recency for the first pattern in the rule essentially. If there is more than one such rule which is matching that same data, it has to be the same data because it has got the same recency, then you use specificity to choose between them. So, tie breaking you do like that. So, this strategy is called mean sense analysis and it has been commonly used in many places. So, let us look at specificity a little bit more. It is a very interesting approach. It allows us to do something called default reasoning, which we will again look at in more detail later. And as the name suggests that you can make some inferences by default unless you know better essentially. So, let me do this with an example. Supposing I have these rules, a rule is called bird, and it says that if something is a bird, then add a working memory element whose class name is can and the attribute name is fly essentially, and the value of the attribute is who can fly essentially. So, you are essentially saying if x is a bird, then say that x can fly essentially. Now, if I can have another rule, this rule says, let us call it a penguin. This rule says that if x is a bird, it is also known that x is a penguin, then so I should really say make, right. I forgot to do that. Let us say cannot fly. So, you can think of can and cannot as things that creatures can do, and the attributes are cannot fly, cannot eat, cannot swim, cannot whatever, and then the value is the individual who can or cannot do that essentially. So, now we have two rules, and the working memory is as follows. Is bird Tweety is penguin. So, you will find that this name Tweety is the most common name in AI textbooks. So, there are these two birds, Peppy and Tweety. What we know about Tweety is that Tweety is a bird. What we know about Peppy is that Peppy is also a bird, and Peppy is a penguin essentially. And I let loose this set of two rules. What will happen? What? Let me see. So, I have two rules. I have three pieces of data. I do the match process. What will be in the match? How many rules will be in the conflict set? There will be three rules. One rule which matches Tweety, which says that Tweety is a bird, therefore Tweety can fly. Another rule which matches Peppy, which says Peppy is a bird which can fly, and a third rule which matches Peppy and says Peppy is a bird and Peppy is a penguin, so Peppy cannot fly. According to specificity, which rule will that Peppy cannot fly, right. So, you can see that I can have, if I want to determine who can fly or who cannot fly, I can have a default rule. The default rule says if anything is a bird, then that thing can fly. But I can also have a rule which is more specific, which says that if something is a bird and something is a penguin, then that something cannot fly essentially. So, in this example, things will work fine. For example, let us say the first execution will be saying that Peppy cannot fly. The second time the rule fires, it will say, let us say Tweety can fly, but unfortunately the third time the rule penguin rule will no longer be in contention because of refractoriness. So, the bird rule for Pepe can fly essentially. Can you see that? That first I will make an inference that Pepe cannot fly because Pepe is a penguin, but because I have this refractoriness criteria, that rule will never come into contention again. So, I am left with two rules which can now compete with each other. One says that Pepe can fly, the other says Pt can fly. So, in some order they will execute because they are roughly equivalent essentially. So, I will first end up making an inference that Pepe cannot fly, then I will end up making an inference that Pepe can fly. How do I get around this problem? So, my first inference is correct, that I am saying that Pepe cannot fly, but because the other rule still exists in my knowledge base, I do not want to make the inference now that Pepe cannot fly. Any suggestions? So, the problem is I can modify the bird rule . So, if I had rewritten my bird rule in this fashion, then this problem will not occur essentially. Now, I am distinguishing between birds which are not penguins. Remember that I have put a knot here essentially. If x is a bird and x is not a penguin, then say that x can fly. Now, you can see that this is all very tricky business. You want to simplify your knowledge representation and you want to simplify your reasoning as possible. So, you want to have default rules which say that okay, anything is a bird which can fly, but then at some point you want to say that okay, if it is a bird, but it is not a penguin, then sorry, if it is a bird and if it is a penguin also, then it should not be able to fly. Then what we have done here is that we have added an exception. We are saying that all birds except penguins cannot fly. Now, obviously, this business of adding exceptions can be very painful essentially. You cannot keep on adding an exception for any such thing essentially. So, later in the course when we look at default reasoning, we will see how we can get around this problem essentially. But for the moment, what I want to really emphasize upon is the fact that specificity allows us to do default reasoning, that if we have more information, we would make a different conclusion. If we have less information, we can make some different conclusions. In this case, if we know that something is a bird, we can go ahead and infer that can think and fly. But if we also know that it's a bird and a penguin, then we can make an inference that it cannot fly essentially. Okay. So, I want to just end with a small example or a program to, since we are thinking of OPS5 as a programming language. So, a program to sort this thing, which is one of the things, just give me a minute, which is one of the things we do most often in computer science is to sort. If you look at what the industry programs do, most of the time they are sorting things essentially. So, the working memory, let us say is looks like this, that we have a record, just for simplicity, then we have an index as an attribute and we have a value which let us say is a number as an attribute, and we have a set of statements which says record 1 value 20, record 2 value 30, record 4 value 50 and so on. You can add things like you can convert this into a student database, student name, let us say rank or something or something, index something, and then marks, value is marks essentially. But essentially we want to say that index 1 should have, that is the problem of sorting, right. Index 1 should have the smallest value, index 2 should have the next smallest value and so on and so forth. So, we can do this as follows. So, P sort if we have a record index I value n, if we have another record index j greater than I value m, let us say less than n, let us say we want to sort in ascending order. What should I do? I can swap the indexes, right. Or I can swap the values, it does not matter, same thing. So, what is this rule saying? That if there is a record with index I which stores a value n, if there is another record with index j which is more than I which stores a value m which is less than n, then just swap their indexes essentially. So, make the first one as record j and the second one as record I essentially. So, and if you see, if you think about this carefully, if you are given a set of 100 records, then by the time this program terminates, by this we mean that it stops matching anything further and then there is nothing else to be done. All the records will be in sorted order essentially. So, just think about this, and it allows you to do these kind of things quite simply. And as computer scientists, we have always been fascinated by simple ways of doing complex things essentially. And some things can be done very simply in ideas like logic programming or rule based systems. But of course, it all comes with a caveat. We are not talking about efficiency here. We cannot give any guarantees of saying that this algorithm will work in n log n time or something, but maybe you should give some thought to that, supposing you were to write such a program for sorting, what is the average case complexity you expect it to be. So, some small exercise to think about. So, we will stop here with forward chaining and rule based systems and ReTNet and things like that. We have been focusing on the algorithm size. So, we will swing to the other side for a little while, and we will come back to first order logic and then see how can we represent what we want to say. So, we have not really paid much attention to logic. We have said okay, you can have arbitrary or ad hoc predicate names, but that will not make sense. If you want to solve real problems, you would need to carefully choose the predicates that you want to say, and we will try to look at these problems of how can we express things that we really want to express essentially. How can we choose predicate names essentially. So, we will spend some time on that in the next few classes essentially. Okay.
With that modified the PT word, the bird.
Modified?
The modified bird definition. Can PT fly? Can you come to a conclusion that PT can fly or not? Like the information of PT being a penguin is unavailable. So can you come to a conclusion that it can fly or not?
Who? Yeah, PT can fly.
It's not a whether it's a penguin or not. It's not
stated, right?
It's not stated.
So yeah, that's an interesting question in the sense that what is the semantics of the negation sign is? The semantics is that there is no record which says that X is a penguin.
It can be or it cannot be. You cannot come to a
No, if there is a statement in your knowledge base that PT is a penguin, then this will not match. If there is no such statement, it will match. So, there does not exist or something like that essentially. So, obviously, you can see that this testing for a negation thing is to be done a little bit carefully. I have not mentioned it when I was talking about the rated network, but you have to be a bit careful, because looking at negation amounts to looking at the entire working memory to see that there is no such record existing. How do you handle that is something that I have skipped essentially.